Okay, so I'm going to walk you through the simulation today. As you can see, I've already started it. You don't have to wait for me to draw all of this, but we have our sun over here illuminating these objects. This is our moon in 8 different locations. 1, 2, 3, 4, 5, 6, 7, 8. And what we're talking about right now are the moon phases. This is just like what the do now that you did on Monday. So I've already gotten the first 2 points here, illustrated the moon, the earth, and the sun during the 8 phases of monthly revolution. The next thing that we're going to want to do is label all 8 phases. So in order to know what it is, how the phases of the moon are, they're not just due to where the moon is at and how much of it is lit up by the sun, but it's also due to the perspective of the observer here on Earth. So if I'm on Earth and I'm looking at the moon, I can only see this half of the moon because it's casting a shadow on itself. So this line right here represents my line of sight. If I'm at that same position and I'm looking at the moon, I can see only this half right here. So I can't quite see all of the illuminated half, but I can see most of it. Again, if I'm at that same point, I'm looking over here, I can see half of that half. Looking over here, I can see just a little bit of that illuminated half. Over here, and I can see none of the illuminated half. You pretty much get the same thing when you're looking in this direction. So this line that I'm drawing, this line represents how much of the moon that you can see because it casts a shadow on itself. Or I guess you could say it blocks itself, this back half of it, from any observer looking at it from one side. So right here, these lines represent the boundaries of our observation. And if you look at how these lines gradually, you see all of it, most of it, half of it, a little bit of it, none of it, and then the process repeats. This right here really explains the phases. So we know this over here, this is our full moon. On this side, when we see none of the illuminated side, this is our new moon. Right here, these two, these are our quarters. When you see half of the half here and here. I'm not really too concerned about first and third and waxing and waning. Over here, this one's easy. When you see a little sliver, this is the crescent. Here and here. Which one's waxing, which one's waning? It really all depends on the direction of your orbit. And this is the hardest one to remember. This will be the one that you may lose a point for on the quiz. This is the gibbous. Alright, so I'm not actually getting all of the 2 points for this one. This part of the rubric, you need to describe what people can see from Earth. So that I just drew the labels. The description, just think about what it would look like from the perspective of the observer when the moon's in this position. They see all of the illuminated side. Over here, they see none of the illuminated side. So that's what your descriptions are going to be about. How much of the lit up half of the moon can be seen? Since you can only see half, how much of that half is going to be illuminated from the sunlight? So that takes care of the first 4 points. Just make sure that you have a description going with each of these. You don't really need a description for each crescent, each quarter, and each gibbous, but make sure that you have. There should be a description for full, for gibbous, for quarter, for crescent, and for new. So there should be 5 sentences going with this picture. Okay, so let's start a new layer, or the next part of your drawing. You're going to have to bear with me as I work through this process. takes a little bit of time, but I think it's good for you to see it. I prefer showing students the process of creation rather than just the final product. At least when I'm in class, that's what I prefer to see, is how to do something, not just what it looks like when you're done. All right, so, but you don't have to do it with this software, which is kind of a pain. So we have our sun back. Before I do that, let me jump to a picture that I wanted to pull up for you. Just if you're struggling with drawing this and my picture isn't doing a good job, you can find everything online. So here are your 8 phases, and this is missing the same thing I was. There's no descriptions for the 5 phases, the full, the gibbous, the quarter, the crescent, or the new moon. But this really shows you the same thing that I just did. All right, so the next part of the rubric is to illustrate and label the sun, the moon, and the earth during the 2 types of eclipses. So let's get our earth drawn here. Draw it a little bit bigger this time. And just to be accurate, here we got our E for earth. Make sure that it has a shadow because the front half is blocking the back half from getting the light. These are the people on the earth in the daytime. These are the people on earth at nighttime. And it takes about 24 hours for them to flip sides, or 12 actually. Alright, so let's do the first, let's do the most difficult one to draw. The first one that we're going to draw is a solar eclipse. Now the word eclipse means block. Solar means sun. So this type of eclipse, the sun gets blocked. And it gets blocked by the moon. So here's our moon right here. So I'm going to pick just 2 light rays, the ones that are the most important. The ones that just skim the surface of the moon. So I got a light ray. This is really difficult to draw with a simulation. And it's hard to draw in general, but with this thing it's even tougher. So this one just barely makes it past. And this one does the same thing on the other side. So right here, there's going to be a little bit of a shadow. Now let's do the same thing coming from the other angle. So these aren't the only light rays, but these are the ones that are the most important for us right now. So we see in this area right here, this is the area where there aren't going to be any light rays making it, because the moon's shadow being casted in this direction and in this direction, this is the spot right here where no light rays are able to make it to Earth. I guess this picture isn't really doing the greatest job at showing what I'm trying to show, but you could also take into account these light rays here. I mean, the more you draw, the more complex and difficult it gets. But let me go back to this picture right here is what I'm trying to show you. So we are looking at the solar eclipse, when the moon blocks light from reaching the earth. And because the moon is so small, it only blocks it totally from one specific point. There is larger areas where there's a little bit of a shadow, but the greatest shadow, or the umbra, is casted right at this point right here. And that's what I was trying to show with this drawing right here, which clearly I didn't do the greatest job. So let me get rid of those lines and just try and show the shadow that gets casted by the moon onto the Earth. So right here would be that shadow. Not a very large area. This happened actually the first day of school. Try to take you outside to see it. There are some of you, but unfortunately it was a foggy day. Who would have thought? So this right here, a solar eclipse, this is when the moon blocks light from reaching the Earth. It doesn't happen every month. You might assume that it did because in the last picture I showed you the moon going around the Earth. Well, the plane of orbit for the moon, when it's in front of or when it's on the new moon side, it's not always exactly in the plane. That the shadow right here sometimes gets casted upwards like this, or downwards like this, or to the right of the Earth or left of the Earth. This is actually fairly uncommon. It happens about every other year, like every 18 months does this shadow actually get casted on the Earth. It's really hard to picture in 2 dimensions. But please refer to this picture on the internet that I'm trying to show you when you are illustrating it. It was difficult for me to draw, but hopefully you saw what it was that I was trying to draw. I'll try to do it one more time, but I might just make it as bad as I did last time. But it's important that you don't just draw a picture here, that you understand how this picture is illustrating what it is I'm trying to show you. So this right here is where the light stops. It can't go past it anymore. So behind these 2 lines, there's a shadow being casted right here. And you also have it coming from this side as well. That's a little bit better. Now, you do have some light peeking out of this end and some light peeking out of this end. There's still a shadow here and a shadow here, but there's a complete shadow right here casted onto the Earth by the moon, which blocks the sun, hence the name solar eclipse. Okay, so let's see if I can back this up all the way. There we go. And get rid of that, and we'll start all over again with the second type. Oops. The lunar eclipse. So this is fairly common. It doesn't happen every month for the same reason that the solar eclipse doesn't happen every month. But it does happen a lot more often, and if you think about why, the Earth's shadow is much larger, so the moon is much more likely to pass in front of it. But in a lunar eclipse, what happened is the moon is getting blocked from sunlight, and what's blocking it is the Earth. So if I draw those rays again, and it's in reality there's a lot more going on than just those rays. But it's just those rays that help us illustrate this process right now. So this ray just barely skims the surface of Earth. Same thing over here. Oh, that was a really bad one. Whoops. Alright, let me draw these rays first and then I'll draw the moon. So here's 2 rays leaving the sun that just barely make it to the Earth. Hopefully I can get it this time. They're not supposed to be curving like that. And here's 2 more rays doing the same thing. Just barely making it past, but everything in between them gets blocked. There we go, that's better. So behind these 2 rays, there's light being blocked. And behind these 2 rays, there's light being blocked. But back here, you can see where a shadow, a complete shadow, would be casted. And this would prevent the moon from receiving any light. It actually would be, let's check that picture that I just showed you back here. So our moon would be back here in this shadow. So a lot of you have probably seen this before. It's much more common. And you might have noticed that the moon looks kind of red when it occurs. Well, the reason why is some of these light rays that are able to just skim the surface of the Earth, they pass into the atmosphere. And when the light rays interact with the atmosphere, they get absorbed by it, and then they get re-released. And when they are released, some of their energy content is absorbed by the atoms or molecules. They vibrate it, get it excited. Some of that energy gets left behind, so the waves actually get stretched out. And you should remember that waves that are in the red end of the spectrum are the most stretched out. They have the largest wavelength, the lowest energy, and that's why sometimes you get something that's called like a blood moon. All right. So let's just compare our two pictures here. Seems like they're a little bit different, but I want to, pretty much the same. I guess they just didn't draw this line right here or this line right here. But you get the picture. The lunar eclipse is when the moon is in the Earth's shadow, and it happens a lot more frequently because the Earth casts a much larger shadow, but it does not happen every month. Keep that in mind. So this whole thing right here, this is the shadow, not this part right here. So excuse my drawing. Okay, so at this point, we are already 6 out of 10 of the way done through the diagram. Let's move on now to the seasons. So I'm going to need a whole new layer for this one. And now I'm going to actually have to draw the whole sun. We're going to zoom out a little bit so that we can see the Earth's revolution around it. Okay, here's our sun. Now let's draw the Earth in 4 different locations around the sun. We'll put it here, 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 and here. Now you might be thinking, hold on, why is it closer here and further here? It's not because there actually are 2 times where it's closer on the opposite side. That's not true. I'm trying to make it look a little bit elliptical. So picture this kind of like flattened out. I'm not looking at it right from above. I'm looking at it kind of from the side on an angle. So here's our elliptical path. All right, so there's really 4 days which separate the seasons. One of those days is December 21st or 22nd. It's called the winter solstice. On the other end, you have June 21st or 22nd. That is the summer solstice for us northern hemispheric folks. Over here, the spring equinox. This is March 21st or 22nd. And then down here, our fall or autumn equinox. That is September. I believe this one definitely is the 22nd. These vary a little bit. It's not like exactly on the day. But let's talk about what causes the seasons. So, the Earth's rotational plane, meaning I guess you could think about the equator, is not exactly in line with its revolutionary plane. There's a tilt. There's a 23 1.5 degree difference between the orbital plane and the rotational plane. So the Earth is actually a little bit tilted here. I should have drew it much larger so that you could see it. But in December, that tilt is facing away from the sun. And in June, that tilt is facing towards the sun. Now, in September and March, that tilt is neither facing toward nor away. So, sorry that my drawing is so small that you're having a hard time seeing it, but that's why I pulled up all these images on the internet. I figured that this wasn't going to go well. Oh, you don't want to see my homework. Okay, so here we go. This is what I wanted you to see and what I was trying to draw. Now they get the autumn and spring, or vernal is what they call spring, flipped around here. And my dates are a little bit different, but don't worry about that. What you really want to worry about is this tilt right here. Notice the Earth's axis, which is the imaginary line about which it rotates, is not exactly perpendicular to its orbital path. That right there is the I guess you could say the cause of seasons, the reasons for the seasons. And it's this tilt right here, this 3.5 degree tilt. So this is what you're going to want to illustrate when you are trying to draw the sun and earth during the days separating the seasons. And I want you to understand exactly why. And this kind of gets to it a little bit, but hopefully some of you are thinking, all right, well, why is it that when the southern hemisphere is pointed towards the sun, we are in the winter time in the northern hemisphere? Or in the summer, why is it that the northern hemisphere is warmer than the southern hemisphere? You might be inclined to think because it's closer. That's actually not true. In the Earth's orbit, it's actually furthest in June. So it doesn't have to do with the distance from the planet to the star. It has to do with the type of sunlight that it's getting. So I'm going to jump back here. Well, actually, let me show you the pictures online first, and then I'll go back to my picture. So since the Earth is tilted away from the sun in the winter, I guess for us in December, you can see that there's much more sunlight getting hit here, and there's much less sunlight over here. There's much more intense. We're going to talk about that a little bit more. And then on the opposite end, in the summertime, there's much more intense sunlight in the northern hemisphere versus in the southern. And it's not just about the number of rays, it's about each of those rays, or a specific amount of sunlight getting spread over a given area. Now, this is a pretty bad picture, but I think it does the best job at explaining or illustrating this process. If you look at these two, I guess rays, you could say, they are equal in length before they hit the Earth. Now, direct sunlight, or light that is coming in at a right angle, it covers the least amount of area, which means it's the most intense. You're getting the most sunlight per square area, versus indirect sunlight. You get it spread out over a much larger area, and that's because the Earth's surface is curved. So as you get up closer to the pole, that surface gets spread out, which is causing this sunlight to get spread over a larger area. So it's less intense. There's less, you could think of it as energy per square meter. That's actually the unit for intensity. It might be power, so it has time in there, but pretty much how much energy there is in a given area. And then last picture, I want to talk about this. This right here kind of shows you what I was talking about. When it gets spread out over a narrow area, it's much more intense. Spread out over a larger area, much less intense. So that's why the snow doesn't melt in the North Pole. It's still getting the same amount of sunlight. It's just getting, or not the same amount, it's getting its sunlight spread out over a larger area versus the tropical regions where it gets focused on one small area. So this direct sunlight, that comes down to why we feel it differently here on Earth. And how I would like you to illustrate that in your drawing, I think it would be a good idea for you to picture this. Okay, so this is, we're talking about in the northern hemisphere. What is it like? Let's just say NH. This is where our sunlight is the most direct. So on a patch of land, we have, let's just say, I don't know, 4 rays of sun spread over this area. I could try to draw it in 2 dimensions, but make things look really messy here. Now in the southern hemisphere, on this same day, you're getting less direct light. So in one patch of space, whereas up here I was able to fit 4 rays, down here you can barely fit 3. So you get more intensity. I should have had these all spread out evenly from the get-go so that you could see it better, but hopefully you're getting the picture. Now over here, it's going to be the exact opposite. In the northern hemisphere, you're going to have the light rays more spread out. So I can only fit about 3 on this patch of land. And then in the southern hemisphere, since it's tilted towards the sun, our light rays are more concentrated. So I can fit many more beams of light on one patch of land. Not many more, but 4 more. So I should have been keeping these of equal distance to make my point, but hopefully you get what I'm saying. Now over here on the fall and the spring equinox equal, you get the same amount. So there's no need to draw the 2 pictures. These days of the year are the same no matter which hemisphere you're on. And the same thing here. The northern hemisphere and the southern hemisphere. Same amount of sunlight or same angle that those rays are hitting the Earth's surface. Alright, so hopefully you get the picture here. Technically I should have drawn like 5 and 5, 3 and I don't know, 4. But you get what I'm saying, hopefully. So the main things that I want you to know for your quiz, it's the tilt of the Earth's axis, which is the imaginary line that it rotates around. It's tilted relative to the orbital path. That is what's causing there to be seasons. But here on the Earth, the main cause has to do with these the angle of the rays coming in being much greater or much more direct in areas where it's tilted towards, and much less direct in areas where it's tilted away. Those are going to be the 2 points. Now, if you illustrate it versus explain it, that's up to you. Some of you are good at remembering these pictures, but make sure you understand the pictures well enough to be able to explain them, because if they're as horribly drawn as mine, I might question whether or not you understand what you're talking about. So it's good to be able to do both. Show it and tell it. Okay, so we're moving on to the last part. The sun, the moon, and the earth, the sun, the moon, the earth, and the ocean during the 2 monthly tides. So tides happen daily. And let me show you some pictures, or one picture real quick to explain that. Tides all have to do with the moon's gravitational influence on the earth and its oceans. So people are always wondering, why is it high tide over here? This is obvious. The moon's gravity is pulling the ocean towards it. But over here, why is it that we're not getting a high tide? Or why are we getting a high tide over here if it's far away from the moon? How come this water isn't flowing to these areas right here? Well, what's going on is the Earth is actually being pulled towards the moon as well. And since this surface of Earth is closer to the moon than the top of the ocean right here, the Earth's surface is actually getting pulled away from the ocean right here. So tides are all about the difference between the strengths of gravity. Gravity is much stronger in areas where it's closer. So over here, it's just tugging on the whole ocean, bringing it closer. But over here, it's tugging on the Earth, bringing the Earth further from the ocean. So depending on which tide of the day, and there's 2 daily tides. Think about it in 24 hours. If I'm starting out right here, it's high tide. 6 hours later, it's low tide. 6 hours later, it's high tide. 6 hours later, it's low tide. And 6 hours later, boom, that's 24 hours. Now, tides actually don't happen every 24 hours. They happen every 25 because in the process of this rotational motion, the moon is revolving. So by the time somebody who started here and makes their way around, by the time they get back, the moon has made its way 1/28th of its orbit around the Earth. So I got a little off track there, but I want you to know that if you are on the side of the Earth close to the moon, the reason why there's a high tide is because of the moon's attraction on the ocean. But if you're on the side of the Earth that's far away from the moon, the reason why there's a high tide is because the Earth gets sunk down and the ocean, I mean, it does bubble up, but it only gets deeper because the Earth got lower beneath your feet. So pretty interesting to think about how tides are due to the, I don't know, the swell of the ocean and the depression of the Earth simultaneously. All right, but let's get back to the assignment, monthly tides. So there are types of tides that happen every single month. One of them sounds like it should happen every single year, but let's get a new layer here, similar to the one that we drew before. So I'm going to draw the sun again. Or not. Okay, now this time we have to draw the earth and the ocean, so be a little bit more strategic about my color choice here. Let's do dark green for the earth. And light green for the ocean. Actually, we should save that for later. For right now, let's put the moon right here. So, without the sun even being there, we know where the high tide's going to be. It's going to be here. And it's going to be here. Alright, so let's see. Probably should have chosen a little bit different of colors. Let's see if I can fill that in without ruining the screen. Nope. Alright, not too bad. Okay, so here's our ocean bubbling up on each side. Should be actually bubbled up a little bit more over here, but you get the picture. So we have our lows here, our highs here. And if I'm a person on the Earth's surface, in 24 or 25 hours, I'll make my way back to the highs. That's why there's 2 highs and 2 lows. Now, we're not talking about daily anymore, though, just reviewing. So here's our moon pulling on the ocean and pulling the Earth away from the ocean over here. Now, when the sun's gravitational pull is in line with the moon's gravitational pull, so we know that the sun is pulling on the Earth in this direction here, So I'm going to draw an arrow here and here, even though we want to think about the Earth being pulled this way and that way. Actually, let's do that. Forget about it. So whenever the moon is in line, either on this side or 14 days later on this side, 2 weeks later, so this is just two different positions that the moon could be, this is known as a spring tide. So when the moon's gravitational pull is lined up with the sun's gravitational pull, this is where you get out of the month the highest high tides, meaning all throughout the month, the tides that are the largest happen when the moon and the sun are pulling on the Earth's oceans together in line. The highest high tides and what you're also going to get here are the lowest low tides. So right here, this is when you're lowest of your lows and your highest of your highs. So get rid of all this text for you. Talk about the final thing that you're going to need to know today, or need to finish today, and one of the things that you're going to need to know on your quiz. Oh man, all right, so jumping back to where we just were, try to get this done quickly. If I'm putting the moon right here, I'm still going to get my high tides on the side of the moon right here, and on the other side of the moon. Oh my God. So still going to get high tides here and here. So when the moon is in this position or in this position, you still have your highs here and your lows here. These are known as neap tides. For neap tides, what's happening is that the sun and the moon's gravitational attraction on the Earth's ocean, or the Earth, because remember, this back end of the Earth is being pulled in towards the sun, and this back end of the Earth is being pulled in towards the moon. Oh man, can't get any luck with this thing. Not that you care, but alright, so whenever these two gravitationals, or this gravitational pull and this gravitational pull, or when it's over here 2 weeks later, when this and this are canceling out, that's when you are going to get the lowest high tides of the month, because they're canceling each other out. And that's when you're going to get the highest low tides of the month. Alright, so once you get done with this, please make sure that you check yourself, and it's always best to have somebody else check you, so that when you try to show it to Mr. H, he doesn't tell you, hey, you forgot to do this. Go back to your desk and get it done if you want to get credit for it. Rather have somebody else tell you to get it done before he checks it, so that when he checks it, you get that 10 out of 10. Alright, hopefully this helps you with the assignment. Don't forget to utilize some of the resources online. There's one that I just forgot to show you. Hopefully helps you see the highest of the highs when they are in line and the highest of the lows when they are canceling each other out. Alright, that's it. Hope you enjoyed the show.